Okay, so in our last class we started talking about the 2-watt meter method for measuring power in a three-phase system. Okay, so let us continue our discussion on this topic. Uh, Suppose we have a balanced three-phase supply and then a balanced three-phase load. It need not be in a star connection, it can also be in delta connection, but nevertheless let us consider only one. Okay, suppose this is A, B and C phases. Okay, so this is also A, B, C, this is N. Now if we have 2-watt meters, okay, how to connect them? Okay, put the current coil of the 2 meters in any two lines. Okay, for example, I can put it here, okay, and the other one may be here. So this is the current coil, this is also current coil, okay, and then the pressure coils, voltage coils should measure the voltage of these two lines with respect to the unused line. Okay, so in this case line number C, okay, and then if this is plus minus, this should also be the plus minus like this. Okay, and similarly here. Now I have to measure the voltage of phase B with respect to phase C, so I can do it like this. Plus minus, pressure coil, pressure coil. Okay, so that's how to connect it. Now let's consider, so this method works no matter whether the load is balanced or not. It only requires the sum of the three currents to be equal to 0. And now let's consider the special case of balanced load. Okay. Achha. Now suppose the phase sequence of the supply is ABC. Okay, then how will the phasor diagram look like? So this may be the voltage VA, VB, VC. You may also call them VAN, BN or and CN. That means with respect to the neutral. Okay, then let us call this W1 and this as W2. Then what does W1 measure? How much will be the reading of W1? So W1 measures the voltage VAC and the current IA, okay, multiplied by the cosine of the angle between VAC and IA. Okay, now VAC is nothing but line to line voltage, okay, call that VL. IA is nothing but line current IL. And how much is the angle between VAC and IA? Okay, suppose these loads are all equal to z angle theta, and z angle theta. Okay, so line current IA will be here, where this angle is theta. Similarly, IB will be here, this angle is theta, and IC is here. So currents also form a balanced system. Okay, so now VAC, okay, that is voltage A minus C, so that will be this line, this is VAC, okay, so which is also same as this line, parallel. Okay, now how much is this angle? Anyone? How much is this angle? This is 120 degree. Okay,
30 degree.
so yeah, so 30, so this is also 30 degree. Okay, so if so, then how much is this angle between VAC and IA? I should have here cosine 30 minus theta.
Yes, sir.
Or theta minus 30. Anyway, cosine is cosine of theta is same as cosine of minus theta, so sign doesn't matter really. And then similarly W2. What will be the reading of W2? W2 measures which voltage? BC. VBC, which current? IB. And cosine of angle between BC and IB. Okay, so this is equal to VL, IL. How much is this angle? Okay, so let us draw VBC, that means B minus C is here. Okay, and so that is same as this line, VBC. Okay, so how much is this angle? It should be cosine 30 plus theta. Okay, because this angle is 30 degree, 30 plus theta. So what we see here, that the two wattmeters, their readings are of the form VL IL cos 30 plus theta or 30 minus theta. One of them will have 30 plus theta, another will have 30 minus theta. Now which one will have 30 plus theta, which one will have 30 minus theta? That depends on multiple factors. For example, phase sequence ABC, if I just change it to ACB, this may change. Also, which lines I am selecting to put the current coils in, that will be a deciding factor. So depending on these things, one of them will have 30 plus theta, another will have 30 minus theta. Which one plus, which one minus, that we cannot say without having the exact circuit diagram. But this is for sure, one of them VLIL cosine 30 minus theta, another VLIL cosine 30 plus theta. Okay? Achha, now let us just check how much is W1 plus W2. So that will be VLIL common. And now let's expand these cosines. Okay, so cos A minus B and cos A plus B is how much? 2 cosine 30 cosine theta. Okay, now cos 30 is root 3 by 2, so this becomes root 3 VL IL cos theta, as expected, because we know that sum of W1 plus W2 should be equal to the total power. Okay, so as expected we are getting the total power. Okay. Achha, now one more thing. Suppose W1 and W2, these two readings are given. From that, can we find out the power factor of the load. We can find out the total power, of course, by adding the W1 and W2, but can we find out power factor? Let us try. What happens if we consider, say, W1 minus W2? How much is that? So we will have VL, IL common, and then cosine A minus B minus cosine A plus B. That is 2 sine A sine B. So sine 30 sine theta. Okay, now if I divide W1 minus 2 by W1 plus W2, how much is that? So we have tan 30 tan theta. That is tan theta by root 3. Okay, so from this you can calculate how much is theta. That will be root 3 tan inverse root 3 W1 minus 2 by W1 plus 2. Okay, so you can also calculate the power factor of the load from the readings of the 2 wattmeters. Is it okay so far? Any question? No? Okay, fine. So maybe we can take up a few example problems. Here is one. Okay. It says while measuring the power of a 3-phase balanced load by 2 wattmeter method, the readings of the 2 wattmeters are 100 watt and 250 watt. How much is the power factor of the load? Okay. I think this is very straightforward. Would you like to try first?
Yes.
Yeah. Okay. So I will just wait for a minute or so for you to try.
So 36.6 degree.
And how much is cos theta?
0.8.
Okay, I think you are right. Yeah. So let us solve. So we know that, I mean, the 2 wattmeter readings are of this form: VL, IL, cosine 30 plus theta, another will be 30 minus theta. Okay, but we don't know which one is 30 plus theta and which one is 30 minus theta. We don't know which one is 100 watt, which one is 250 watt. Okay, so but anyway, we can then write this, that as we saw, W1 minus W2 divided by W1 plus W2, it was tan 30 tan theta. So tan theta and tan 30 is 1 by root 3. Now, since we don't know which one is W1, which one is W2, but W1 plus W2 is definitely 350 watt, but the numerator may be either 150 or minus 150. Okay, so let me put a plus minus 150 watt, because we don't know which one is W1, which one is W2. But now tan theta will be plus or minus root 3 times 15 by 35, that means 3 by 7. Okay, so from this you can calculate how much is theta. Tan inverse root 3 root 3 by 7 with a plus minus ambiguity. But however, since we need cos theta, it doesn't matter whether we have plus or minus. Okay, so that will be, if you calculate, you will get 0.8. Okay, any question here? No? Okay, fine. So here is another question, and these two questions are actually similar, same. The first one says that while using 2-watt meter method for measuring three-phase power, it is found that 1-watt meter reads half of the other one and both positive. How much is the power factor? The second question says that 1-watt meter reads twice of the second. How much is the power factor? So it's the same. One reads the half of the other, or the other reads twice of the former. It's the same. How much is the
Plus
power?
minus 30, plus minus 5 or 6.
Yeah, right, you are right. Okay, so how do we do this? Once again, we know W1 minus 2 by W1 plus 2, that is 1 by root 3 tan theta. Now, we don't know which one is W1, which one is W2, but it may be like that. W2 is equal to 2W1, so the denominator will become 3W1 and the numerator will become 1 times plus or minus W1. So this is 1/3. Okay? And if so, then that means tan theta is plus minus root 3. So theta is 60 degree plus or minus, and that means cos theta is half. Cos 60 degree, am I correct? Yeah.
Tan theta is 1 by root.
Sorry. I
Plus
have a
or minus.
mistake here.
Yes, sir,
Yeah,
1
yeah.
by root.
This is 1 by root 3 here. Okay, so this is 30 degree, and then this is root 3 by 2. Now it seems correct. Okay. Fine. So
Sir, but it asked the angle.
pardon?
The question asked the angle only.
Oh, question asks the angle. Okay, yeah, then plus or minus 30 degree. That's the answer. Yeah. Okay, so now again a three-phase balanced load with a power factor of this is basically 1 by root 2 is connected to a balanced supply. Power consumed by the load is 5 kilowatt. We have to find the reading of the 2-watt meters. Okay, if we use a 2-watt meter method. Okay, so how do we proceed? So we know that cos theta is, this is nothing but 1 by root 2. So I mean, this is 707. So that means theta is plus minus 45 degree. Okay. Now, next what else do we know? The readings of the 2-watt meters are of the form VL, IL, cosine 30 minus theta, and VL, IL, cosine 30 plus theta. Theta already known. How much is VL, IL? Okay, so for that we can use the total power. So we can write that root 3 VL, IL cos theta, this is equal to 5000. Okay, so that means VL, IL will be 5000 by root 3
Root
into
6.
root multiplied by root 2, right? Root 2 goes above. Okay, so that's VLIL. Now you can put the value of this VLIL in this equation. Okay, so this 2 will therefore be 5000 root 2 by root 3 cosine. One of them will be 75 degree, another yeah. So now which one is which one, that we don't know, but anyway, so 75 one of them, another will be this. Which one is which one, that we don't know, but anyway, so you can find out what are these two readings. Okay, fine. Is it fine? Any question? Okay, now then let's take this one. This is very interesting actually. Okay, so we have 3 wattmeters and 3-phase balanced load with 400 volt line to line voltage, and here a balanced load, balanced supply and balanced load. Okay, now what is given? Line to line voltage 440, sorry, this should be 440. Just a second, let me check. 440 or anyway, doesn't matter, whichever you take. Okay, 440, yeah, fine. Now there is a switch here. Okay, and this switch can either be connected, S can be connected to N or S can be connected to Y. It is given that when this switch is in position N, then all the 3 wattmeters read the same value, 577.35. Okay, so, and we have to find out what will be the readings of the 3 meters if this switch is connected to Y. Okay, now here the polarities are not given. Let me give you the polarities to make it little easier. But anyway, even it is not given, you can still solve it, but let me give you the polarities. Okay, now what can you infer from this given question? Okay, first this switch is connected to position N. Okay, then how are these 3 wattmeters working? What are they measuring?
VIL cos theta, VL cos theta.
Individually they are measuring what? Okay, so you see, if I call this IR, IY and IB, so they are measuring 3 line currents, and which voltage they are measuring? This is measuring now which voltage? First one, W1, VR,
VIR into first.
which voltage? VR
And
With respect to
Neutral.
with
sir.
respect to neutral. Okay,
VRL.
yeah, and this one is measuring Y, N, V,
N.
B, N. So, and we have a balanced load. Okay, so you may think there is a star connected load inside. Okay, ZA, ZB, ZR, ZY and ZB all are equal. Now what does W1 measure? It measures the power consumed by ZR, right? Similarly,
Yes, sir.
yeah, the neutral is also connected. Okay, even it is not, even if it is not connected, since the load is balanced, it doesn't make any difference. Now W2 is measuring Therefore, Z power consumed by ZY, and W3 is measuring power consumed by ZB. So when in position N, W1 plus W2 plus W3, that is equal to what? Total load power, which is 3 times this number, because they all measure the same value. So the 3 times this is approximately 1732 watt. Okay. Achha, now what else? In the question it is given that the volt ampere, total volt ampere is this. Okay, in 3-phase system, total volt ampere is defined as, or apparent power is defined as √3 VLIL, which is given 3436 volt ampere. Okay, so if, and total power is nothing but √3 VLIL cos theta. If so, how much is cos theta? Okay, so that will be
Nearly almost.
pardon, almost, yeah, 0.5. Okay, so 1732 by 3436, it's 0.5, which means theta is 60 degrees. Okay, so this much information we can get from the readings when the switch is in position N. Now when the switch is in position Y, then what will be the readings of the 3 wattmeters? Let us start from W2. What will be the reading of W2? What is the voltage that this wattmeter is measuring now? Okay, this will, all these voltages will change. What does W2?
0.
Yeah, so this measures 0 voltage. So how much is W2 reading now? Okay, so for position
0.
Y, W2 is equal to 0, right? Because the voltage across W2 is 0. Okay, acha, if so, then what does W1 and W3 do? What are they doing? I mean, is the
With respect to Y.
with
circuit.
respect to Y? So is this configuration a familiar configuration of W1 and W3? This is
Yes, sir. 2 watt.
just like 2 wattmeter method, because W1 is measuring IR and voltage of R with respect to Y, and W3 is measuring IB and voltage of B with respect to Y. So this is just like 2 wattmeter method. So therefore, what can we say about W1 and W3? For example, W1 and W3 together should be the total load
7.
power, okay, which we already know. Now, how much is W1 and how much is W3? Okay, so for that, we have to draw a phasor diagram. Okay, and in the question says the phase sequence is RYB. So let us draw a phasor diagram. VR, VY, and VB. Achha, now W1 is measuring which voltage? R2Y. Okay, so Y minus R minus Y, so that is, this is the voltage VRY for W1. Okay, acha. And for W3, which is the voltage? B minus Y. Okay, B minus Y is here. And now the currents. Okay, so we know the value of theta is 60 degree. And what else is the load? Yeah, the load is inductive. Okay, so how should be the line currents? The line current IY should be here. This angle is 60 degree. This is IR. Okay, then IY will be here and IB will be here. Now from this diagram, can you tell the value of W1 or W3? Let me refine my diagram a bit.
866.
Yeah, so how much is the reading of W1 say? W1? So W,
866.
pardon? No,
They won't be equal.
yeah, they won't be equal, right? But how much is the reading of W1? So W1 is measuring IR, VRY, okay, and the angle between them. So from the diagram, can you see how much is the angle between IR and VRY? This angle is
90 degree.
90
90
degree.
degree.
Okay, anyway, because VRY is at here at 30 degree, okay, VRY is at 30 degree, IR is at minus 60 degree, so their angle, the angle between them is 90 degree. So how much is the reading of W1?
0.
W1 is 0 because cos 90 is 0. So how much is then W3?
30 degree.
Right, 1732 with total power, and W2 is 0 anyway. So that's the answer. So is it okay? Achha, let us do one more exercise, okay, just to strengthen our understanding a bit more. Let me copy this. Okay, now suppose I change the star connected load into a delta connected load. Okay, and suppose I also change the phase sequence, maybe A, C, B. Okay, however, they are still balanced, Z angle theta, Z angle theta, Z angle theta. Now, can you find out the reading of the two wattmeters? Suppose the line to line voltage is also given VL. How much will be the reading of the two wattmeters? Question. Given VL, how to find out W1 and W2? How to start? Start with a phasor diagram. Okay, so now we have A, C, B sequence. Okay, now first thing, we need IA, IB and IC, okay, but before that we may need to calculate the phase currents. Okay, so suppose this is IAB, IBC and ICA. How to find out these currents? To get IAB, we need VAB. Okay? How much is VAB? VAB is this voltage. Okay, so which we may also draw here. This is at an angle of 30 degree. This is VAB. Okay, then how is VBC? BC will be B minus C. Okay, so B minus C will be upwards. Okay, and then VCA for this current, VCA will be C minus A. C minus A is like this. Okay, so that will be here VCA. Okay, so we have AB, BC and CA. Next what? Let us find the currents IAB, IBC and ICA. Okay, and so these magnitudes are for these three line to line voltages are VL. So this is also VL. Okay, this magnitude is also VL. Okay, Acha. Now IAB will be, so if we assume theta to be positive, IAB will be here. This angle is theta. Okay, then IBC, BC will be here. This is also theta, and ICA is here. This is also theta. Okay, and we can say that the magnitudes of IAB, IBC and ICA, they are all equal to VL by Z. Correct? Okay, then next what? Next we need the current IA, IB and IC, line currents. Okay, so how to get the line currents so IA is equal to IAB minus ICA. Correct? AB minus CA. Okay, so where will that line be? AB minus CA. Okay, so that is this line. Okay, so that will be here. This is IA and this angle is 30 degree. Correct? Please check. Then what about IB? IB is IBC minus IAB. Okay, so BC minus AB. Where is BC? BC is here minus AB. So that is this line. Okay, so which will be now it's getting a bit difficult to draw here. Because I haven't done it very accurately, so difficult, but anyway, still try it. So this is IB. I'm really not sure whether IB is on the first quadrant or on the second quadrant, okay? But what I can say that maybe according to my drawing it may be little further. This angle, how much should be this angle? This is IB, okay? Between
30.
yes? This
30
should 30 degree.
Sir, it will depend on theta, right? Whether
It
it
also
would be in
depends,
first
yeah, it
quadrant.
also depends on theta. Okay, so, right. So, if so, then let us find out how much will be the, how much will be the reading of W1. W1 measures which voltage? VAC, which current? VAC, IA, and cosine of angle between VAC and IA. Okay, W2 measures BC, IB, cosine of the angle between VBC and IB. Okay, now let us see whether we get the correct values. So VAC for W1 is equal to VL. How much is IA, magnitude of IA? Magnitude of IA will be root 3 times the phase currents. So that is VL by Z. Okay. And how much is the angle between AC and VAC and IA? Okay, VAC is here, this is VCA, so that means VAC will be opposite. So that will be somewhere here, VAC, and where is the angle IA? Okay. Now, what is the phase angle of VAC? How much is the phase angle of VAC?
60 degree.
This is it 60? So this is VCA is at minus 120. Okay, so yeah, you're right. So this is 60 degree. Okay, so this is 60 degree, and then IA is here. So what is the angle between IA and VAC? What is the phase angle for IA? Okay, so let me. So this is yeah. So this is, wait a second. This is at 0 degree. Okay, VA is at 0 degree. Then this line is at minus 30. Okay, then this is then minus 30 minus theta. Okay, minus 30 minus theta, and then this line is at minus 30 minus theta plus 30. So this is at minus 30. So IA is at minus 30. So therefore,
So that would be only 30 degree, not 60.
Just a second. So this becomes 60 minus, sorry, 60 plus theta. Just a second, if I'm correct. Do I have any mistake anywhere?
Yes, sir. That green color 60, that should be 30 there.
The green color should be 30. Why are you saying that?
So because the greens are at 120 with each other.
Yes, so that means this green, this dark green is at
Yes, sir.
oh yeah, you're right. So yeah, sorry. So this is at minus VC at minus 120. So this dark green is at minus 150. Okay, so if so, therefore this is at 30. Yes, you're right. This is 30. Okay, so then this is also 30. Okay, so similarly you may also find out how much will be the reading of W2. Let me do it quickly. So voltage is VL, current is again root 3 VL by Z. Okay, now how much is the angle between VBC and IB? VBC is here, okay, and so VBC is at 90 degree straight up, okay.
31 is theta.
Let us just verify. So this is 90 degree, and the other one IB. What is the angle of IB? IB IBC is at
121 is
90
theta,
minus
IB.
theta. Okay, just a second. So IBC is at 90 minus theta, and then plus 30. Okay, so 90 minus, so we have 90 minus theta plus 30. Okay, and then this is at 90 degrees, so minus 90 degree. Okay, so that is the angle. 90 goes there, so 30 minus theta. Is it correct? Please check. Okay.
Yes, sir.
Yeah. So I mean, I thought I just have a bit of time, so I thought let us do a thorough exercise, which will also be a good practice for all of us. Okay, fine. So that's it for three-phase systems. Now, yeah, okay, so so we have discussed 3 topics so far, 3 major chapters, DC circuits, then sinusoidal steady state AC circuits, and one special case of that was three-phase three-phase sinusoidal circuits in steady state. Okay, so these 3 we have discussed. Now, since this semester we have very little amount of time compared to other semesters, so therefore a few small topics which are there in the books, in the notes shared with you, which are also there in syllabus, but they being very simple things which you can study on your own, I have skipped them. Okay, for example, I mean, I'm just mentioning a few of them. The definition of form factor of a periodic waveform. Okay, then crest factor or peak factor. Okay, so this kind of things are there which you can study on your own. So do you know what is form factor? This is the ratio of
Don't know, sir.
RMS value by average, half-wave average value of a periodic Okay, so similarly, this is RMS below and peak value above. Okay. Please check these definitions, and these are simple things which you can study from the books or the note on your own. So these things we have skipped, okay, because these are very easy. Similarly, some other small things are also there. One another example which I remember is quality factor. Okay, for resonating circuits. Let us briefly discuss this for a series RLC circuit for series resonance. Okay, so if we consider a series R, L and C, let me draw the resistance here. And if we apply a source, AC source with variable frequency, okay, so variable omega, fixed RMS value, then, and suppose here I connect a voltmeter, okay, to measure the voltage across the resistance, okay, and then if I draw a graph of the input frequency omega versus voltmeter reading, you know how it looks like. How does it look? So it is a graph like this. This frequency is called the resonating frequency, where j omega L and j omega minus j by omega c, they are equal and opposite. Okay, so omega is equal to, call it omega naught 1 by root over LC. Okay, and then this circuit behaves like a filter. Why I say so? Because you can think that you are applying different frequencies at the input. Okay, so this is the input and voltmeter reading is the output. Okay, so for some frequencies voltmeter reading will be very small or very close to 0, and for some frequencies you will get some large value of voltmeter reading. So as if some voltages are allowed to pass, or some frequencies are allowed to pass from the input side to output side, and some frequencies are blocked. So in that sense this is called a filter. Okay, and this is also called a band pass filter. What does that mean? It means that it passes or allows some frequencies within a small narrow band near omega naught, near the resonating frequency, and all frequencies further from these resonating frequencies are blocked, are not allowed. That's why it is called a band pass filter. Okay, now we can ask how good this filter is. As a filter, if we treat it as a filter, how good or how precise this filter is. So to measure that, we first need to measure the bandwidth of the filter, that is the width of the region of the frequency which is allowed to pass. Now you can see that this is not a discrete or this is not a discrete graph, this is a very smooth continuous graph. So I cannot say that certain frequencies are passed and certain frequencies are absolutely blocked, because we can see that, okay, omega naught is allowed to go, pass at the maximum extent, frequency 0 and frequency infinity is not allowed at all, but these frequencies here and here, they are allowed to some extent, not completely allowed, not completely blocked. So how do we define the width of the pass band? Okay, so for that, the way we do it is we measure the power, okay, at this middle value, central value, omega naught. Okay, how much is the power here? Okay, so how much is the power at this point? Power that goes up to the output point, that means across the resistance. How much is the power received by the resistor at this point? Anyone? If the RMS value is V, then how much is the voltage across the resistance VR at the resonating frequency? VR will be equal to V. Okay, so here the power is therefore proportional to VR square by R, you can say. Okay, then at this point the power is somewhat less. We will find out the point where the power is half of the maximum power. Okay, so that point is called as the cutoff point. Okay, similarly here at this point also the power is VR square by root 2, whichever is that point. Okay, that point is called another cutoff point, and between these two region is called the pass band. Okay, because in this region the power going to the output side is maximum. Okay, I mean much larger than the power for these regions. Okay, so therefore the middle region is called the pass band, and this width is called the bandwidth. Okay, and these two frequencies, this one is called the cutoff frequency or half power frequency. Similarly, this is another cutoff frequency. Okay, now let us find out how much is the bandwidth for this filter, or how much or what are these cutoff frequencies. So we know omega naught, the central value is 1 by root LC. Okay, if I call this W1, this point, and this is W2, okay, then how much is say W2? Let us find out that. Okay, what we can say at W2, the total impedance of this circuit, RLC circuit, should be how much? R plus j omega L plus 1 by or minus j by omega C. This impedance should be how much? This should be R times root 2. Why? Because if it is R times root 2, okay, so at the central point, at this frequency, how much is the total impedance? Just R, because j omega L and minus j by omega c, they will cancel each other. So at this point, at omega naught, the impedance is R. Okay, therefore at omega 2, the impedance should be R root 2, because if that is so, then the current flowing here will be how much? 1 by root 2 times maximum current. And if the current is 1 by root 2 times maximum current, then the power will be half of maximum power. Okay, so therefore this magnitude should be R root 2. Is the logic clear to everyone? Anyone with any doubt? Okay, so if not, then tell me what should be the magnitude of omega L minus omega C?
R.
It should be R, absolutely right. Okay, because, yeah, so that's right. So now if so, then we can write omega square L, I'm just taking the, yeah, just multiply this. So omega square L C minus omega R C omega minus 1. This should be equal to 0. Okay, and what else? Now, which one is larger at omega 2? Okay, this is for omega 2. This is for omega 2. Which one is larger, omega L or 1 by omega 2c? Which one is larger at omega 2? Achha, at omega naught, which one is larger, omega L or 1 by omega c? At omega naught?
Equal.
Equal. Then at omega 2, which one is larger?
L
Omega
Omega
L, sir.
Okay, so here L is larger. So here omega 2L should be greater than this. Okay, now from this, can we find out the value of omega 2? This is a quadratic equation, so we may write it this as L R by L omega 2 minus 1 by L C. This is equal to 0. So from this, what do we get? Omega 2 is equal to R by L plus minus root over R by L whole square plus 1 by L C whole divided by 2. Okay, so we have two possible values of omega 2, but are both the values possible? I mean, both plus minus signs are both possible here. What will happen if we consider minus sign? Then the value of omega 2 will be, what can we say? It will be negative. Yeah, so it will become negative. So that's not possible because we are considering positive frequencies. So therefore, this minus sign is not allowed here. So that is the value of omega 2. Okay, so we got the value of omega 2. Now let us find out the value of omega 1. How can we do that? Any idea? At omega 1, how much is the total impedance? How much is this? Again, this should be root 2 times R. because here also the power is half. Okay, so if so, this condition is same as the previous condition. But what is the difference between omega 2 and omega 1? Anyone? In omega 1, 1 by omega 1c is larger than omega L. Okay, so that's the difference. So here we will have 1 by omega c minus omega L, this quantity. Okay, this should have a, now 1 by omega c will be larger, and this magnitude should be equal to R. Okay, so from this you can again find out the value of, okay, this is omega 1, 1, 1, 1. Okay, now again we can find out the value of omega 1 as before. So we can write again similar equation we will get. If we simplify this, we will get omega 1 square LC plus R C omega 1 minus 1 equal to 0. That means omega 1 square plus R by L omega 1 minus 1 by L C. This is equal to 0. This equation is same as this previous one, except here we had minus R, here now we have plus R. Okay, so what will be the solution? Omega 1 will be minus R by L plus minus root over R by L whole square. I did a mistake in the previous one here. Do you see that? This should be 4. 4 by LC here. Okay, now once again, is both plus and minus signs possible? No, because we are considering positive frequency, so this should be plus. So W1 is this, W2 is this. So how much is the bandwidth then? W2 minus W1, so that will be, if you subtract, you will get R by L. Okay, now one last thing here, quality factor. Okay, so this is a measure of the goodness, how good this filter is as a filter. Okay, so for a good filter, what we may expect? We expect that only a particular frequency is passed and all other frequencies are blocked. Okay, therefore that means the narrower this pass band is, the filter is better, the filter is more selective. Okay, so therefore we want a smaller bandwidth. So therefore quality factor is defined as something divided by bandwidth. And what is in the numerator? In the numerator we have the cutoff, or the central frequency, you can call omega naught. Okay, so the thinner this filter is compared to the omega naught, the better the filter is, or more selective the filter is. So that's the definition of quality factor. Okay, so therefore now this omega naught is nothing but 1 by root LC, and bandwidth is R by L. So here we have L by R, which is root L by CR. That's the expression for the quality factor for series resonance circuit. Okay, similarly you can discuss the same thing for a parallel resonance circuit, which I will leave for you to study from the book or the notes. Okay, fine. So any question so far? Anyone? Any question? Otherwise, I will take up a new topic. We can.
Sir, can you please show the quality factor on?
Okay.
Sir, it should be 1 by or total by 0.
Oh, yeah. Thank you. Okay. So next we shall study about mutual inductance. Okay, please listen very carefully. If we have one coil, inductance L, okay, and the voltage across it is Vt, current through this is It. What is the relation between V and L, V and I? According to these symbols and this sense of current and voltage, Vt is L di dt. Okay, so here also I. So the end through which current enters has the potential of plus L di dt with respect to the other one. Okay, so here L is of course positive. L is positive. I mean, otherwise it doesn't make sense. Okay, now if we have two coils, okay, so they are close by. Okay, so physically you may have like one okay, here we may have one coil like this, and maybe there is another coil also together. Okay, so now if a current is flowing in one coil, call that I1T, then it will create some flux. Okay, the flux lines, part of the flux lines may be like this, and if I1T is changing, this phi is also changing, and this flux also goes through the second coil. Therefore, there will be also a voltage induced in across these terminals of the second coil, call that V2. Okay, so now in a circuit, okay, when we draw a circuit diagram, we may just draw two coils like this. One coil here, and maybe in some other place the other coil is shown. Okay, and here suppose the current is I1T. Okay, and then there will be some voltage drop, voltage induced in both the coils. Okay, so in the coil 1, red coil itself, there will be a voltage which is L1, if this coil has a self-inductance of L1, di1 dt, this side plus, this side minus. Where do we have this plus? On the end through which current enters. Okay, but there will also be some voltage in the second coil. Okay, call that, and that will again be proportional to di1 dt. Okay, and let the constant of proportionality be m. M is called the mutual inductance. Now the question is which side, so this is the magnitude of the voltage, okay, or yeah, but I mean, is it the voltage of the left side with respect to the right side, or is it the voltage of the right side with respect to left side? Any idea? Okay, so that's not possible to tell. I mean, we can't tell it. How do we tell that? Okay, so because I mean, in this diagram, we don't even know how and where these coils are actually there. Because in circuit diagram, this is just a schematic. So how do we know which side should be plus, which side should be minus of this voltage? So therefore, we use what is called a dot convention. This is a convention used for drawing circuit diagrams. And what do? We put two dots, like maybe here for one coil and maybe here for another coil. So two dots on two particular sides of the two coils which are mutually coupled, which are mutually linked. And what does this dot signify? It means that, okay, if the mutual inductance between the two coils is M, okay, so I should use some suffix M 2 1, okay, that is the inductance of coil 2 due to coil 1. So this is coil 2, this is coil 1. Okay. So if the mutual inductance between them is M21, then M21 di1 dt is the voltage, is the potential of the dotted side with respect to the non-dotted side, provided the current is entering through the dotted side of the other coil. So that means here this side should be plus, this side should be minus. What I said, let me just write it. Okay?
Repeat.
Yeah, I'm repeating. Okay, if current enters through the dot of one coil, then the potential of dotted side with respect to the non-dotted side of the other coil is M, whatever, M1221 di1 dt. Okay, if current enters through the dotted side of one coil, then the dotted side of the other coil will have plus M di1 dt voltage with respect to the other side. Okay, so is this clear?
Yes.
Okay, so if so, a quick exercise. Suppose I have two coils, one here, another here, okay, and I put dots arbitrarily, maybe here and here, and it need not be actually dot. Any common symbol you can use, in like a square, whatever, any common symbol you can use. Okay, and now suppose the current is, here is di1 dt. The mutual inductance between them is M, okay, or say M21. Okay, then the question is, and if this voltage is Vt plus minus, then how much is Vt? Anyone?
M21 di1 by dt.
M21, yes, right. Okay, why is that so? Because first we see that I1 is going out of dot. So you may say that actually, sorry, here this is just I1. So you may say that this is minus I1 going through the dot. Okay, so therefore this dotted side should have M21 d minus I1, so minus di1 dt. Okay, this side with respect to this side. So that means if I just, I mean, this minus and minus can cancel each other, so this is the result. So is it okay to everyone? Achha. Then next let us assume that now first we have one coil, the inductance is L, the current through it is I, which is a function of time. Okay, and then to pass this current we definitely need some source outside, which I am not drawing. Okay, and that source may need to apply some voltage to pass to start this current. Okay, so let me just call this voltage Vt. Now we want to calculate the energy stored in the coil. Is how much? How do we know that this coil has some energy when there is some current? How do we know that it has energy? Okay, one way of verifying that is that you take this coil, okay, and pass some current, okay, and below this you put a block of iron, okay, and if this is on ground, now if there is no current, nothing's going to happen. But the moment if you have some current, then this coil will act like a solenoid electromagnet, and it will attract this iron and it can pull it up. So it can do some work. Okay, so that means it has some energy, it gains some energy when it has a magnetic field associated to it, which can do work, which can pull things up. Okay, so that's why we know there is some energy if there is some current in a coil. Okay, however, when there is no current, that point we can say energy is 0. Okay, energy is 0 when I is equal to 0. Just call it I, because then it cannot do any work. But then how much is the energy for any other value of current? To find that, we can do it in this way. Okay, so power input to this coil is how much VTIT. Okay, so initially suppose there is no current and then some current is established. So we need some source outside which have to apply some voltage. Then only, only if we have some non-zero value of Vt voltage, then this current will start to change and this current will start to flow. So we need some voltage, and at that moment, at any moment when this current is increasing, the power input is Vt-It. So energy input is Vt It dt for any infinitesimal time interval, and then we can integrate it over time, starting from 0 time when there was no current to the final value of time when the current is settled down to a fixed value. Okay, so once this current becomes fixed, then di dt is 0, so voltage will be 0, no further power input is required. Okay, so suppose It is changed or increased from 0 to capital I. Okay, then how much is this total energy? So this will become integration of V is nothing but L di dt multiplied by I into dt. Okay, and now L is constant, you can write it outside, and then this is nothing but so this dt you can cancel, and you can write it as d of I square integrated for over I equal to 0 to capital I. Oh, but divided by 2. Okay. Do you agree? Why is this so? Because d of I square is what? Apply the product rule of differentiation, you will get di into I plus one more di into I. Okay, so we will get 2 di into I. Here we have this dt you can get rid of. So here we have only 1 I into di. So how much is this? Therefore, finally, L by 2 constant. After the integration, this becomes I square. So that's the expression of energy stored in a coil. Okay. Now, if so, now consider two coils which are mutually coupled. Their self-inductances are L1 and L2. Okay? And suppose the current here is I1, here is I2. How much is the total energy stored? Okay, so suppose this is I1 is capital I1, I2 is capital I2. How much is the total energy stored in the coil, in these two coils? Oh, we also need to show some dots, otherwise the diagram is not complete. Okay. Now, to calculate the energy, let us think in this way that before that, how much is the mutual inductance? Okay, so if I call this voltage V2 plus minus and V1 plus minus, okay, so we have the relations that V2 is M21 di1 dt when I2 constant. Okay, and similarly, if I1 is constant, then V1 is M12 dI2 dt when I1 is constant. Okay, so M21 is the coefficient for voltage induced in second coil due to rate of change of current in the first coil, and so on. Okay, so now in general, if both I1 and I2 are changing, can you tell me what do you think should be the expression of V1? It should be, if both the currents are changing, it should be
di2 by
L1
di1
by dt plus M12 this voltage plus the self-induced voltage di2 by dt, and similarly V2 is L2 di2 by dt plus M21 di1 by dt. Okay, now total energy stored, total stored energy is how much? Okay, we will find this out in smaller steps. Okay, so first assume, so step 1, okay, keep I2 equal to 0 and increase I1 from 0 to capital I1. This is the first step. In this step, how much energy is required? Okay, so now power input at any moment is how much? So in general, I can write this is equal to V1 I1 plus V2 I2. It's always true. That's the power input. Okay. Now, for this particular case, V2 I2. Okay, when I2 is kept 0 and I1 is increased from 0 to I1, then how much is the power input? So I2 is 0, second term will not be there. Okay, and so first term will become, so how much is V1? V1 is L1 di1 dt plus M12 di2 dt. That's V1. Okay, and multiplied by I1, okay, plus 0 because I2 is 0, and anyway this is also 0, di2 dt is also 0. So what do we have here? L1 di1 dt multiplied by I1. So energy input will be how much? So for that we have to integrate L1 di1 dt multiplied by I1 into dt. Okay, this power input is integrated over time, and this, as we have just calculated previously, it will come out to be half L1 I1 square. Am I correct? Next, step 2. Okay, so let me copy this diagram. Keep I1 equal to I1 constant and increase I2 from 0 to capital I2. So for this situation, how much is the power? Let me calculate the energy directly. So energy input, so that will be integration of the power. So the power is in general V1 I1 plus V2 I2. Okay. Now, how much is V1 here? V1 in this case will be L1 di1 dt. In general, it is also true M1 2 di2 dt. That's V1 multiplied by I1 plus L2 di2 dt plus M21 di1 dt. This is V2 multiplied by I2, okay, whole multiplied by dt. Now a lot of the terms are 0 here. Okay, so for example, I1 is kept constant, so this term is 0. Okay, what else? This is 0. Okay, so we have two terms left. M12 M12 I1 di2 dt plus L2 I2 di2 dt. Okay, let me write dt here, plus and dt. Now I1 is kept constant in this step, so basically this is capital I1. Okay, and so this is constant, I write it outside the integration. So therefore the first term, what will be the integration of the first term? Anyone? M12 I1 and then I2 is increased from 0 to capital I2, so that's I2 plus, and the second term is again similar to this integration we did. Okay, so that will be half L2 I2 square. So therefore the total energy stored is how much? This term, this energy which required in step 1 plus this energy which is required in step 2. So that comes out to be half L1 I1 square plus half L2 I2 square plus M12 I1 I2. Okay. Now, so any questions so far? Achha, now tell me how much energy is required if we increase I2 before I1. Okay, so in this previous derivation, we first increased the current I1, then kept I1 constant and then increased I2. If we do it in the opposite order, I2 first, then I1, how much will be the energy? What will change? What do you think? in this expression. I mean, one thing you can say, I will just change 1 and 2 everywhere in this derivation. Wherever I have 1, I will make it 2, and wherever I have 2, I will make it 1. I can copy paste the entire thing and just swap 1 and 2. So if I do that, so what will I get? So I will just get the same thing here, except M12, I will get M21. But now it seems that we are getting two different expression for energy for the same physical condition. Okay, both the coils have same current. They started from same zero current, and we see that the energy required is different. Is it possible? It's not possible, because you have same
No, sir.
physical state. Okay, so if it is the same physical state, that means what do we need? We need M12 to be equal to M21. If this is not so, then there is some serious problem. What is that? Okay, acha. So, for example, here, what did we do? We first increased current I1, then increased I2. Okay, now suppose I decrease I1 and then decrease I2 to 0 again. Okay, so I mean the steps are like this. First, increase I1 from 0 to capital I1, then increase I2 from 0 to capital I2, then decrease, okay? So increase, then decrease I1 from capital I1 to 0, and then decrease I2 from capital I2 to 0. In this process, how much energy is required? Or how much net energy?
Right.
So it should be 0. So it should give total energy required equal to 0. Okay, and if M12 is not equal to M21, we will get, we will get a term like this, M1, previously we got 1, 2, right? 1, 2 minus M21 multiplied by I1, I2. This will be the overall energy gain in a closed path. I mean, we started from all zero currents, we reached the finally all zero currents, same state, same initial state, same final state, but there will be some energy gain. Okay, this may be positive or negative. I don't know. If it is positive, that means we are generating energy, which is violating energy conservation. And if it is negative, I can do this in reverse order, I2 first and I1, then it will be positive, and it will then still generate energy. We cannot generate energy. So that's not possible. We can't generate energy. So therefore, we definitely need M12 to be equal to M21. Okay, so that is one thing that we learn here. Acha.
But it is already like we have a theorem na, that M12 is equal to M21, that mutual induction depends only on the orientation of the coils.
Basically this is a theorem. Okay, so here we are proving the theorem.
Okay.
Okay, yeah, fine. Achha, so what next? Acha, next, we have still about 6-7 minutes. Okay, so next one more thing. There is a limit. So let us just call this equal to m, because both are same. Acha. Now, one more thing. If I just copy this diagram and let me paste it. Okay, so suppose I just change the dot positions. Then how much is the stored energy? Then how much it will be? It will become half L1 I1 square plus half L2 I2 square minus m I1 I2. Okay. So previously it was half L1 I1 square plus half L2 I2 square plus m I1 I2, because m12 is same as m21, which is same as m. Okay. Now here we will have a minus sign. Why is that so? You can just do the same derivation. Okay. What are the things going to change? If I just copy these equations, what is going to change here? This will become minus. Okay, and therefore if you just carry on the same derivation, finally here we will get a minus sign. Okay.
Sir, where is this energy stored? Half Li square plus.
Where is this stored? I can't answer that question. It's somewhere there
Sir,
in the
I
nature.
think it is stored in the field around the coils.
Yeah, you can say
Magnetic
that.
field.
And the field is extended over the infinity. Okay, so it's throughout the universe. Achha. Now next. Now just consider this expression of this energy, Control C, Control V, copy paste. Okay, so this must be always greater than equal to 0. Okay, because 0 energy is the state when there is no magnetic field, no ability to do any work. And if there is some magnetic field, no matter in which direction that is, it can still do some work, it can still pull up objects. So the energy is positive, it can do work, it cannot be negative. Okay, now from this we can find some bound on the value of m. Okay, how to do that? For that we will first write it in the form of a square terms. Let me do it in this way. Let me take half common, then we have root L1 I1 square, I1 minus root L2 I2 whole square. Okay, so we get L1 first term, second term, plus we have what do we have here? 2 root L1 L2 I1 I2 and minus 2m I1 I2. Okay, so this should be greater than equal to 0. Now this term I can make it 0. We can make it 0. Can make 0. by suitably choosing the value of I1 and I2. Okay, and therefore it implies that M should be less than or equal to root over L1 L2, because then this term must be positive or 0. Okay, so that means the value of M is bounded by root over L1 L2. Okay, so that's another constraint. And then in general, so now we if we call this ratio M by root over L1 L2 equal to K, this is called the coefficient of coupling, and this is less than equal to 1. Okay, because M is less than root over L1 L2. Okay, and so this will be 0 if the two coils are very far, I mean not mutually linked at all. Okay, then mutual inductance M will be 0. So K is, let me write in this way, 0 less than equal to K less than equal to 1. And if the two coils are perfectly coupled, okay, then it is possible that, I mean, one particular case is, as I have drawn here, if the two coils are exactly situated at the same position, same orientation, then it is possible that the magnetic field of one coil cancels the magnetic field of the other. Exactly, they can cancel each other. Okay, so therefore overall there will be no magnetic field at all, and that means the overall energy stored will be 0. So that means this quantity will be 0. Okay, and this quantity will be 0 means this term will be 0. That means M will be equal to L1 L2, root over L1 L2. That is when they are perfectly coupled, and then K is equal to 1. Okay, so with this I stop here